Hey, Niam and friends. Thanks for reaching out to me on this question. Um, I I love doing math during the summer, and I love to help out. So, thanks for reaching out. I want to say a few things. Good news, bad news. The bad news is that you've not been taught the right tools in order to complete this question. But the good news is I'm here to help, and I'm excited to teach you one of the key fundamental elements of calculus, which what this problem has. So let's begin. This problem begins with a waffle cone or a waffle, and I have my waffle right here. And this person wants to make sure that they're getting the most ice cream in this waffle. And so what they've done is they've got their circle waffle. Hopefully it's a little bit more tasty looking than this. But then they've cut a radius into it. So you can tell I've kind of cut a radius into it. And so what they're trying to figure out is, okay, as I fold this over, what's going to give me the maximum amount of ice cream? Now, some things that you should notice here. This is probably not going to give you the max amount of ice cream. Why? Because this person's not folding it over enough, right? This isn't going to give me the max amount of ice cream. Just like, let's see if I can keep turning this and turning this and turning this and turning this and turning this. Just like this probably isn't going to get us the most amount of ice cream, right? Because this is too skinny. And believe it or not, there's actually an optimal amount, or there's an optimal fold that gives the most amount of ice cream, somewhere between it being really being barely folded over at all and being super folded over. There's actually a perfect amount that gives the most volume, right? Because that's what we're talking about here. We're talking about volume. And so if I were to guess, it's probably looks something like that. That's just kind of my guess. But the beautiful thing about mathematics is we don't have to guess. We have tools to find out the answer to this. So before I begin, there's some things you should notice, okay? To begin, we're going to call this the slant height. And then I want you to imagine a line going from the tip all the way down to the middle, like straight down, boom, straight down from the top. And that's the height. Okay, so as I turn this, I want you to look at my slant height. Look at my slant height. As I turn this, my slant height is not changing. I can fold this over a lot or just a little, but my slant height is not going to change at all. However, my height from the top to the bottom is changing, right? If I fold it out like this, my height is pretty short. If I fold it over a lot, my height is a lot taller, right? So my height is changing while my slant height is constant. As a matter of fact, my slant height is the radius of this circle. So we need to know that, and we need to know that before jumping in. So let's go ahead and jump in. I love problems like these. So I've kind of drawn my figure. And so what I'm going to do is I'm going to label my slant height as L. And I'm going to call the height straight down. We'll call that H. And then we'll call this distance from the middle to the outside. We'll just call that R, because that's like the radius of that top circle, not to be confused with the radius of the original waffle. So, and then what I'm going to do is I'm going to imagine just cutting straight down, and I'm just going to look at this triangle specifically. In other words, if I slice this cone straight down, I want to look at this. You kind of have to get a little creative in imagining with me. but you're actually going to get a right triangle where this is R, this is H, and this is L, right? So I'm just taking this triangle and really looking at just that slice, if you will. So some things that you need to know is that the volume of a cone is 1/3 pi r squared h. Yeah. And then I'm going to use this information over here because this is going to be helpful a little bit later. But I know that using Pythagorean theorem, that h squared plus r squared is equal to L squared. So I want my volume, instead of having two different variables here, I want that to have just one variable. And so what I'm going to do is I'm going to subtract h squared from both sides, and I get r squared is equal to L squared minus h squared. And now I'm going to substitute this in for r squared. So now I have the volume is equal to 1/3 pi L squared minus h squared times h. Now, you might be saying that's not in one variable, that's in two variables. Now, be careful, because remember that demonstration where we saw that the slant height wasn't changing? Well, my slant height is actually a constant, meaning no matter how much I fold this guy, my slant height always stays the same. So yes, you may see a variable here, but just know that that's a constant. They didn't tell us what it was, but it is a constant. The slant height is a constant. So I'm going to rearrange this a little bit. 1/3 pi h times L squared minus h squared. And I'm going to distribute. And I get this equation here. Now I'm going to graph this and I'm going to show you what this means. But this is my volume given in terms of the height and the slant height. And so because the slant height is a constant, actually, let me just go here. Because the slant height is a constant, in this I put in 10 for the slant height, just so we can come up with a visual. But notice what this graph is showing. My x-axis represents the height of the cone. My volume is represented on my y-axis. And so this kind of makes sense, right? If the height is very small, in other words, you barely started to overlap the cone at all, my volume's not going to be very much. And then as I wrap, the height continues. But if my cone gets too high, my volume begins to decrease. And we saw that as I kind of demonstrated it. So there's like this middle ground of where the volume is optimized. It's maximized, I should say. A matter of fact, it's right there, that point. Now, this only represents when the slant height is 10. Our job is to find out what the maximum is when we don't know the slant height. So now we're getting into what's called a derivative. Okay, and so what I'm going to do, this part may not make sense to you, but we are going to take the derivative with respect to the height. And so what a derivative is it represents the rate of change, which I'll go into a little bit more later. And so what the rate of what our derivative is going to be 1/3 pi L squared minus pi h squared. Okay, and now again, this part won't make sense to you. This is actually really easy to do once you learn the techniques. I would probably encourage you to look how to take a derivative and the tricks how to take a derivative. But this represents the slope at any point. So what that means is I can use this formula. Think back to your graph. I can use this formula to find the slope at any point. And the slope at any point can be represented by a tangent line. In other words, like for right here, this tangent line would look like this, which represents a slope at that point. But if I want the maximum volume, which we know is at the cusp or the vertex, the slope of the tangent line here is going to be 0. In other words, my tangent line is going to be flat at the maximum. And I know that this equation, which is the derivative, is represents the slope at any point. So we want to know, when is this slope equal to 0? Because when it's equal to 0, I know that I have a maximum. So what we're going to do is we're going to set this equal to 0, 1/3 pi L squared minus pi H squared equal to 0. And now I'm going to add next step, I'm going to divide by pi on both sides. Next step, I'm going to take the square root of both sides. Now, normally here, I would take the positive and negative case, but since we're dealing with height, I know it has to be positive. So H equals L over the square root of 3. Now, so an alarm might go off in your head saying, oh, I can't have square roots on the bottom. Don't worry about that. But we need to understand what this means. This means that if you want the maximum volume of your cone, the height, which is this guy, has to be the slant height divided by the square root of 3. That's what this is saying. That no matter what cone, if you want the maximum volume, the height has to be the slant height divided by the square root of 3. If we look back to our example, remember I put in 10 for the slant height. Well, if you divide 10 by the square root of 3, you're going to get 5.774. And so this is, how you find the maximum volume. Again, I know that this is a very new subject, new idea, taking the derivative. It's much easier than what I just did. And it's like another lesson for another day, or I would highly encourage you to YouTube it, because you're gonna use it so much in calculus, and it's a fundamental concept in calculus. But what this derivative does is tells us the slope at any point, or in other words, it's also the rate of change at any point. Okay, so anyways, I hope that was helpful. Please keep the questions coming as you go through this. If you need help on this, I'd be more than happy to help. I love helping out, and I love doing math in the summer. It keeps me on my toes and my skills up to date. So anyways, I hope that was helpful. I will talk to you later. Bye-bye.